Hi to all. I am A.V. Laxman Rao, Assistant Professor in Physics, Department of H&S. In today's session, I am going to explain you about origin of energy bands formation in solids. See, in this session, I am going to explain mainly about what is the root or cause for formation of energy bands, especially in solids. Solids I am taking, and in solids, what is the reason behind formation of energy bands? This concept I am going to explain, and at last I am going to explain about the analysis of interatomic spacing versus the energy bands. These two topics I am going to explain in today's session. Now, before going to explain about the root or cause or the main reason for formation of energy bands in solids, first let me explain which are called solids, which materials are called solids. We know that solids are the materials which will have definite shape. Solids will have definite shape. This definite shape they are getting because of all atoms in a solid are packed closely together. Atoms are packed closely together, and there is a bonding between each atom to atom, its neighboring atoms, and when we bring that material into a condensed state, then in general a solid will form. Due to this reason, it will have a definite shape that already we know. So overall here we must understand that a solid will have a definite shape and atoms are packed closely together. So that material is called a solid that we know. Now the thing is, what is origin? Origin is nothing but the main root or cause. It is nothing but it will explain about the cause behind happening of formation of energy bands. The main cause of formation of energy bands, especially in solids. That is the main topic for this session. Here, which are called energy bands, that also we must know. Energy band is also in general called as a band. Now, for example, if you take a solid, in general, bands are forming. Here, band is nothing but a series of energy levels when they were closely packed together. A series of energy levels when they are closely packed together, and it looks like a single energy, that is nothing but a band we are calling it as. So, what is a band we know, and what is the origin, the meaning of origin we know, and which materials are called solids, that also we know. Now, some basic things also we must know before going to know about the origin of energy band formation in solids, such as about the electrons. We know that electrons are responsible for electrical and thermal and optical and other properties of any material. Now, if you take in an atom electrons, here few electrons are called as the valency electrons. Which electrons in general we are calling as valency electron, that we must know. Now, to understand about that, I am taking an atom here. In this atom, the center is nothing but the nucleus, and here orbits are around that nucleus. We have a multiple orbits as like that you take. Now, innermost orbit if you take, some of the electrons are located, and middle orbit you take, some other electrons can also be expected to be occupied in that orbit. Now, you take the outermost orbit. This is the outermost orbit. If you take this outermost orbit, whatever electrons are located in that outermost orbit, we are calling these electrons as here valence electrons we are calling. Okay. So, in an atom, the outermost orbit electrons in general called as the valence electrons. Now, free electrons are also there. Which electrons are called free electrons? Means we can say that here valence electron is this one, and in nucleus, which is the positively charged, in between there will be some bonding is there. Weaker bonding, might be it is weaker bonding only, but thing is there is some bonding between them. Now, when you apply some external energy, as in the form of thermal or the light energy, then these electrons, valence electrons, initially they will absorb that energy and they will get excited, and due to that absorbing the external energy, they will become as now the free electron. Free electrons does not have any bonding with nucleus. They are freely move within the metal. Such type of materials we are calling as free electrons. Valence electrons are nothing but the outermost orbit electrons, and free electrons are nothing but when the bonding will break, then a valency electron is becoming as a free electron. Now already I have explained about what is a band. Here in this case, this is nothing but a band. Here a series of energy levels which are closely arranged and looks like a single energy, then it is called as a band. In solids, now our target is to know how the formation of these bands will be there. Then now that we are going to know. Okay. Now when you know the bands, there are two different types of bands are also there. We are calling them as conduction band and valency band also. We have two different types of bands are there. So conduction band is nothing but the band which is corresponding to the free electrons. In general, in conduction band, we are expecting that free electrons will be located in that conduction band. And the band which is corresponding to the valence electrons, or we can say the bonded electrons, are the holes, that is nothing but called as the valency band. Okay. Now if you take a graph as like this, on y-axis I am taking the energy levels. Valency band is having the lower energy level, and the conduction band is always is the higher energy level when you compare with the valency band. So these are all nothing but how many different types of bands are there, and what is band, and which electrons are called valence electrons and which electrons are called free electrons. So this is the prerequisite to know about the main concept, that is origin of energy band formation in solids. Okay. Now let us move to the actual topic, that is formation of energy bands in solids. Now to understand about this concept, I am taking here three different cases. This first case is nothing but figure 1, and the second case is representing here with figure B, and the third case I am representing with figure C. Now in the first case, let me take here one atom, a single isolated atom I am taking, which is located in a material. A material consists millions of billions of atoms, that we know, in which electrons are there, and especially in solids we know that all these atoms are packed closely together. It is nothing but here, due to this packing of atoms together only, it will have the definite shape. Now I am assuming that there is one material in which a single isolated atom is there. Assume that a single isolated atom is as like that. So this is the nuclei which is positively charged, and let us assume that whatever the electrons are there in that atom, they are revolving around the first orbit as like this. Now here let us assume that one orbit is there and one electron is moving around the nucleus. When you take as like this, I am taking this atom as an isolated atom. The meaning of isolated atom is it is not interacting with its neighboring atoms. Single alone atom is there, no interaction with other atoms. Then such type of atom we are calling as a single isolated atom, in which there is one electron as like this. Since this electron is revolving around the nuclei, it will have its own wave function. So the energy level corresponding to this single electron, here energy level corresponding to this electron within this wave function will have a discrete energy level, will have a certain range value of energy. So that energy you take here as E1. E1 is the energy of electron which is moving in a single orbit in a single isolated atom. Now you take the case B, that is nothing but figure B you take. In place of a single isolated atom, I am taking two atoms, two identical atoms, atom A, and this is also type of atom you take as a atom A only. Two identical atoms, let us assume that in a solid we have two atoms are there and they were closely packed together. Due to this, what is happening? Closely packing of two atoms in a solid, outermost orbits. This is an outermost orbit for this atom and this is an outermost orbit for this atom. These two are overlapped here. Outermost orbits are overlapping. Due to this overlapping of outermost orbit, whatever the wave functions of the first electron in first atom is there, and the whatever the wave function of the second atom in second electron in second atom, they are also going to be overlapped. Due to this, the energy levels which are corresponding to the wave functions of atom 1 and atom 2, these two are also have the approximately equal energy levels. Since overlapping, we can expect that they will maintain a very small gap as the difference between the energy levels. For example, if you take E1 is the energy level of the first orbit electron in first atom, and E2 is the energy level of the second atom electron in the first orbit of the second atom. So by taking as like this, these two are very closely packed as like this. Now in case of you take three atoms, similarly if you take as a three atoms, here three atoms are all these atoms are identical atoms only. Let me take the outermost orbit as like that. When they were packed closely together, here all these wave functions are of the electrons of three atoms are overlapped, and the energy levels which are corresponding to the wave functions of these three atoms are also packed closely together. So energy levels when they were closely packed together, first atom electron energy level, second atom electron energy level, and the third atom electron energy levels are also very closely packed as like this. So the difference between these three will be very less as like that we can take. All this is happening because of in solids atoms are packed closely together. Due to that, the orbits are also going to be overlapped, in which electrons are there which will have some certain range of energy levels. They are also having the almost equal energy levels. Now I have taken here three atoms. If you take in a solid, n number of atoms are there. If you take an atom which is having n number of atoms, if you take the first single isolated atom, this is the case. If you take the two atoms, then this is the case. If you take the three atoms, this is the case. And if you take the n number of atoms which are located in a solid, then we can say that each energy level of an atom are also splits into n levels of energy. Due to that, n number of energy levels which are also here packed closely together. Due to this reason, for this outermost orbit, a band is going to be formed. A band is going to be formed due to this all outermost orbits of all the identical atoms in a solid. So this outermost orbit, whatever the band was formed, in general we are calling it as the conduction band. Now the middle bands, middle orbits and the lowermost energy levels of the bands, if you take, they were also located bottom of this band. So this is called as the conduction band, which is corresponding to the all the free electrons, and the whatever the energy bands which are formed due to the lower energy levels of the bands, they are nothing but here can be expected as in the middle they will be located, and the lowermost band energy we are calling it as the valency band we are calling. So like this, by taking a single isolated atom and by taking here two identical atoms in a solid and three atoms, and the case which here we have to take as, since a solid will have n number of atoms, n number of energy levels are going to be overlapped and are splitted into n levels of very short range energy levels. We are calling it as a band. Like this, in solids, energy bands are going to be formed. Now observations based on this concept, what we can say. So the levels are so close together that they form an almost continuous band. Here if you take three electrons in three different atoms of identical atoms, they are very closely packed together. That's why we are calling it as a band as like this. So it is forming as a band as like this. Okay. Now very important thing is how we came to know that the width of the band, how it is going to be changed. Width of the band cannot be expected for all the bands. That width is going to be increased as the orbits of an atom are far away from the nucleus. It is nothing but lowermost whatever the energy band is there, which will have the here sharp energy band. It is nothing but that width of that band is lower value, and as we are moving away from that nucleus, outermost orbit if you take, whose width of the band will be increased. So that width of the band depends on what parameter means. Here we can say that that is the degree of overlapping of electrons. As the electrons are, as the orbits are overlapped more and more, we can expect that the width is going to be change. As the adjacent atoms are very closer to one and each other, then also can be expected that here the width of the band is going to be change. Okay, so that is very important, and the bandwidth is larger for the outermost atomic electrons. Innermost orbit electrons band, that width of the band, when you compare with the outermost atomic electrons band is going to be increased. The width of the band is going to be increased. So this is very important concept in this energy band formation in solids. Now let us move to very important one, that is analysis part. Analyzing. We are analyzing how that bandwidth is going to be created for three different types of materials. All the three materials I am taking as the solid materials only. As the first type of materials I am taking as metals, and the second type of solid materials I am taking as semiconductors, and third materials I am taking as insulators. Now on x-axis, to analyze here interatomic spacing versus the energy band, how they are very closer to one and each other, that conduction band to the valency band, that I am going to explain by using this graph. On x-axis I am taking the interatomic spacing of the electron. Electrons are atoms we can take. Now interatomic spacing let me take as R, and on y-axis let me take the conduction band and the valency band. If you take metals, it was observed that as the interatomic spacing between atom to atom is very small value, we can expect that the conduction band whatever is there, it is going to overlap on valency band. Due to this reason, whatever the gap should be there, that gap won't be there between these two bands, conduction band to valency band. The gap is going to become as 0. Why? Because conduction band in which free electrons are there. A metal if you take will have a large number of free electrons. If it has a large number of free electrons, is nothing but it is dominating the bonded electron system. So due to that reason, in metals the energy gap is going to be taken as 0. Band gap here, conduction band to valency band, whatever the gap is there, which is called as energy band gap, that is going to become as 0 for the metal. Since in metals free electrons number is dominating, that's why. Now if you take the semiconducting materials, as the interatomic spacing is increasing, here in semiconductors partial value of this band gap can be expected. Partial is nothing but not as low as 0 when you compare with the metals, and as high as insulators. In between the gap can be expected. For example, semiconductors example, for example you take as silicon, or for example you take germanium. Silicon, that energy gap value is given as 1.1 electron volt, whereas in metals energy gap value we know that it is 0. Whereas if you take germanium, this is 0.6 to 0.7 electron volt can be expected. It is partial value. In semiconductors, interatomic distance, according to this we can say that they will have the partial energy band gap as like. Now if you take the insulators, in insulators all atoms are packed closely together and no free electrons are available. That's why the conduction band can be expected as empty, and the valency band in which we can say that all the bonded electrons are there. It is nothing but this whatever the band is there, valency band, it is dominating on the conduction band, whereas reverse it is happening in metals. Due to that reason, in insulators, we can say that valency band is dominating nothing but bonded electrons only are there, no free electrons are there. With respect to interatomic distance, we can say that EV is dominating on EC in insulators. Due to that reason, a large value of gap can be expected. So this line to this line, if you take this line to this line, if you take, a large gap is there. So this that's why energy gap in insulators can be expected as approximately 10 electron volts. Very high value they will have. And semiconductors like silicon and germanium, if you take, they will have the some range of values as partial values as like that. And in metals, we can say that conduction band is overlapping on valency band. That's why no gap can be expected. So this is the analysis of this in three different types of solids based on their electrical conductivity, if you take as like that, we can say. So overall, we can say that because of formation of bands here and the by measuring the energy band gap, we can classify the materials into three different types. As the first type are called metals, and the second type are called semiconductors, and the third type are called here insulators. So this is happening because of formation of energy bands in solids. Based on the energy band gap, we are classifying the materials into three different types. That is the main advantage with this concept. Now, as I told to you, if you take conductors and insulators and semiconductors based on energy band gap, how they were classified into three different types. Here you see, I am taking energy values on y-axis, and valency band bonded electrons are there, and in conduction band free electrons can be located. Now in metals, we know that in conduction band free electrons are there, they are dominating the valency band. Due to that, the energy gap is going to become as a 0. That's why no gap is shown between the conduction band to valency band. Now, based on this band theory only, based on this, we can say that in insulators, whatever the electrons are there, all these electrons are here bonded electrons only. That number is dominating the free electrons in insulators. So due to that reason, a large gap is there between the valency band to conduction band. So it is equivalent to 10 electron volt. Energy gap, if you take as Eg equal to 10 electron volt, and in conduction band energy gap is 0. And if you take the semiconducting materials, valency band to conduction band, whatever the gap is there, we can say that it is a partial value it will have. That's why they were called as semiconductors, we are calling. So different materials will have different energy band gaps. So this is we can explain by taking the main concept as formation of energy bands in solids. Now conclusion. What is the first point? We can say that how the energy bands are going to be formed. So energy levels, when they were packed closely together, then it looks like a single energy level, and the result of that is a band is going to be formed. Okay, and in solids, as I told to you, second point, we can say that atoms should be atoms are closely packed together, and the orbits are going to be overlapped. And the third one is valency band formation and the conduction band formation. So when these two bands are formed, in general in conduction band, we are expecting that free electrons are located, and in valency band that bonded electrons in general will be located in valency band. And last and very important one is, based on this concept, based on the band theory, we are classifying the solids into three different types based on the Eg value. That Eg value, if it is varying as 0 to some value, then based on that we are classifying. If you take as like that gap based on the band gap, we can say conductors, insulators and semiconductors as three different materials. So this is about formation of energy bands in solids. Thank you.